Good morning, everyone. Here we go with one more new topic called atomic nuclei, or we can call in shortcut it's a nuclei. It's a nuclei. We know that here from the previous class we have been studied about the of an structure of an atom, along with along with various various atomic models. Atomic models. Among those atomic models, the one of the good result which is obtained from the Rutherford's atomic model was suggested that there is an centrally centrally located located hardcore hardcore material called nucleus. This nucleus is going to be having positive charge. This nucleus is going to be having positive charge. From the scattering experiment, we got there is a good results about an nucleus. Okay, here this nucleus is going to be consisting of what? And protons and neutrons. Protons and neutrons. As the first assumption we found from the Rutherford's alpha scattering experiment, which is established, that is the mass of atom is concentrated with the small charged region at the center. We call this as a nucleus. Therefore, this nucleus was going to be having a small structural analysis. Just you can see over here, this is we call as the atom, and these are the positively charged protons. Around this, in a definite orbit, there is an electrons are going to be revolves. All these basic things have been discussed in the previous class as well as in the regular classes there. Now we go with the main point of the chapter. It is the first one, that is what we call as a neutron. So first question we have, why the neutron is going to be having an zero charge, or you can call as a electrically neutral. Why this is going to be like this? Why neutron is electrically neutral? As you studied in the basic fundamental classes there, it is going to explain that it is consisting of what? Subatomic particles. It consisting subatomic particles. In the nature, you found there is more than hundreds of subatomic particles. There. Among those hundreds of subatomic particles, we considered, and there are directly take part in the formation of a matter. So there is a directly take part in the formation of matter. These are called as a proton, neutron, and electron. These are called as a fundamental. And now here we are going to be having the main motto is to first go with what is a neutron. We are saying that according to electrostatic, neutron is an electrically neutral charge particle. It is, and this is neutral. There is a presence of a quark. It is, the quark is called as a fundamental elementary particle. There are two types of quark you have. One is up quark, another is a down quark. So up quark is going to be denoted by plus 2/3 times of electronic charge and minus 1/3 times of an electronic charge for the down quark. Here, so this up quark and down quark, in the formation of one neutron, there are two down quarks and one up quark are present. So up quark is denoted by up arrow mark, down quark is denoted by down arrow mark. Now you find this, if I going to substitute these values, minus 1 by 3 times of electron plus 2 by 3 times of electron minus 1 by 3 times of an electron. If I simplify this by taking the LCM, you can just look out here, it's minus 1e plus 2e minus 1e. And you can just see here, there is no charge is present. So there is a charge on the neutron is 0. Hence, we can say there is a neutron is electrically neutral. And it was discovered by, it was discovered by Chadwick. It was discovered by Chadwick. Don't get confused. Proton was discovered by Goldstein. And the nuclear atomic model was given by the Rutherford. Electron was discovered by J.J. Thomson, and neutron was discovered by James Chadwick. A free neutron outside the nucleus is unstable. You remember this point? Here there is an important point we are going to talking about that. So a free neutron outside the nucleus is unstable, it doesn't going to have any stable character outside the nucleus and decays into, and it will be nuclear. So this neutron is going to be decays into proton and electrons. Therefore, how it will be getting there? See, if I go with a chemical reaction or the equation which represent there is a formation of an electron as well as the proton along with an anti-neutrino. See here, there is a neutron is going to be having 0 charge there. So neutron is denoted by the 0 charge, and now here it gives you there is an hydrogen. This is what we call as a proton. This is the proton we have. Along with this, and a negatively charged particle we call as an electron. This is the beta particle we call as an electron. Along with this, we get there is an anti-neutrino. So then the next characteristics which is related to the neutron is neutron, as I discussed in the earlier, neutron is electrically neutral. Then mass of a neutron. So this is mass of a neutron is always equals to 1.6570 into 10 to the power minus 27 kilogram. That is as same as that of the proton mass it is. So mass of proton is 1.6570 into 10 to the power of minus 27. So similar to this, the masses will be remains as it is, unchanged. The next one, its spin angular momentum. As you know very well, angular momentum is always denoted by L is equals to mvr. This is we call as angular momentum. Whereas the linear momentum is denoted by P is equals to m into v. This is for linear cases. This is for angular cases. For example, this is we call as a angular displacement. The angular displacement is denoted by the theta. And we know that angular velocity is denoted by omega is equals to rate of change of angular displacement is called as angular velocity. The angular value will be denoted by this condition now here. Therefore, as you know very well, angular momentum is a vector quantity, mass is a scalar, velocity is a vector quantity, radius vector is also vector quantity here. And if I remove this, you can get there is an L is equals to mvr sine theta. If theta is maxima, that is nothing but what? Moving perpendicular. Then theta is 90 degrees, sine 90 is always maxima. Hence, the angular momentum associated with a moving particle is always maxima. If it is along the direction, theta is equals to 0, then there is no angular momentum is possessed by the given moving particle there. Similarly here, this angular momentum associated with the given electron or the given charged particle inside the atom in a definite orbit. See, we have these are the respective orbits with which an electron is going to be revolved. So this is we call as a positively charged central hard core material, and these are the electrons which will be revolving in a definite orbit, and hence its spin. So why the spin is there? The spin is going to be causes there is a magnetic property. The spin is going to cause us a magnetic property, orientation and the spin, which causes there is a magnetic property or magnetic behavior here. Then its value for the spin is given as the spin angular momentum. The spin angular momentum associated with this charge is given as 1 by 2 half into it's a Planck constant divided 2 pi. This is the formula which are used to determine the spin of the spin angular momentum associated with a charged particle it is. And the SI unit for this is joules second. The SI unit for this is joules second. Then magnetic moment associated with the neutron. How much is what is the magnetic moment? Magnetic moment of a given charged particle, that is what you call as a given neutron is given as. What is the magnetic moment? As we studied in the previous class, magnetic moment is always denoted by capital M is equals to, it's a product of a current into and a cross section area. As you know very well, current into cross section area is called as a magnetic moment, and the SI unit for the magnetic moment is, it is called as ampere meter square is the magnetic moment. This magnetic moment of a neutron is given as, it is 9.57 into 10 to the power minus 27 joules per Tesla. This is the magnetic moment associated with the neutron. Then its half-life, as you know very well, half-life is nothing but what? Is a time taken to disintegrate. So remember, it's a radioactivity concept we have. It's a radioactivity concept we have. It's a time taken to disintegrate half of its original atoms is called as a half-life of a radioactive sample. And this half-life of a radioactive sample is given as, in terms of half-life of a radioactive sample or the half-life of a given neutron is given as for the 12 minutes. Half-life period of a neutron is about 12 minutes. Remember, the half-life time for the neutron is 12 minutes. And now the most important property associated with the neutron, that is the penetration power. Penetration power of a neutron is always highest than the alpha and beta particles. As you know very well, alpha is a little bit stronger than the beta. Beta is a little bit having the much more penetration power than the gamma. That's why gamma is going to be having highest penetration power as comparing to beta and alpha. If I go with a decreasing order, that is what you call, gamma is going to be having highest power of penetration, then comparing to beta, then comparing to alpha, beta is having stronger, comparing to beta, gamma is having highest penetration power. Therefore, now there is a types of nucleons. So there is a types of neutrons. As you know very well, neutrons are of two types. One is called as slow neutron, another is a fast neutrons. So we have two types of neutrons. One is called fast moving neutrons. Another is called as the slow moving neutrons. Both are fully capable of penetrating the nucleus and causing artificial disintegration. Remember the word, both are going to be capable of creating artificial disintegration. So they are able to produce an disintegration character there. Both are going to be having the disintegration character there. And now we have types of atomic nuclei. As the types of atomic nuclei. There is a types of atomic nuclei. Here, the nuclei has been classified on the basis of an number of protons. The nuclei are classified on the basis of number of protons. Remember the word, it is going to be classified on the basis of number of protons. Therefore, it is also called as what? An atomic number. Atomic number. Therefore, among them, the first one is called as a isotope. Isotopes. As you know very well, isotopes are the one where we find there is same atomic number. You find there is a same atomic number and the same atomic number, but the different masses, but different mass number. It's having different mass number. As you're going to get the first best example for this, you get what? H1, then H12, H13. There is a hydrogen, deuterium, tritium. And the second one you find there is an oxygen, oxygen 8, 16, oxygen 8, 17, oxygen 8, 18. These are the examples which are related to the isotopes, as the isotopes are the one which will have the same atomic number but the different mass number is called as what? An isotopes. Is called isotopes. Then second one we have there is an isobar. It's a isobars. Isobars are the one will have the same mass number. Will have the same mass number but different atomic number. Mass number is same, atomic number is different. Then we know that it's a H13, then helium 3, 2 is the best example. Or you can go with one more best example for this is carbon 6, 14 and nitrogen 14, 7. These are the best examples for isobars. Then third one we have isotones. We have isotones. Isotones are the one which will have the equal number of neutrons. Equal number of neutrons. It is going to be having equal number of neutrons. Then the best example for this is beryllium, barium 9, and this is 4, boron 10, and this is 5. And one more example, carbon 6, 13, nitrogen 14, 7. So these are the best example for isotones. Then we have the size of the atomic nuclei. The next concept we have there is a size of atomic nuclei. The size of atomic nuclei. So here we have to know about what is the size of the atomic nuclei. The first one we go with the nuclear radius. Nuclear radius. The nuclear radius is given as what? Radius is proportional to a to the power 1 by 3, or it's a cube root of mass number. Therefore, radius is directly proportional to a to the power 1 by 3. Then remove this proportion value by putting some constant value. R is equals to R naught into a power 1 by 3, where R naught is called as the corresponding the average distance. R naught is given as 1.2 into 10 raised to minus 15 meter is also called as R naught is equals to 1.2 Fermi meter. Then second one we have the second property of the atomic nuclei is first property of atomic nuclei is nuclei radius. The nuclear radius is always directly proportional to the mass number, that is the cube root of the mass number. If I remove this proportion value, we get there is an R naught value is 1.2 into 10 raised to minus 15, or you can write in standard way it is R naught is equals to 1.2 Fermi meter. Then second one, it's a nuclear volume. We have there is a nuclear volume. The second important character of the nucleus is nuclear volume. You know very well, volume of a nucleus is given as, because the nucleus is going to be considered as almost a sphere. The volume of a sphere is V is equals to 4 by 3 pi r cube. 4 by 3 pi r cube. But as we calculated already the value of R, substitute in the volume equation. V is equals to 4 by 3 pi. It's a R naught cube a to the power 1 by 3 into 3. So 3 get cancelled. Then we get the answer as V is equals to 4 by 3 pi r naught cube into a. Hence 4 by 3 is constant, pi is constant, r naught is also constant because r naught value is 1.2 into 10 raised to minus 50. This is also constant. Only this a is variable. That is the mass number is variable. A is called as what? Mass number is variable. So hence volume is directly proportional to A. Volume is directly proportional to what? A. Then next one, the third property of atomic nuclei is, the third is atomic nuclear property. What is the third property of the atomic nuclei is, we have there is a nuclear density. It's a nuclear density. The third important character is nuclear density. As you know very well, if I go with the triangular physics, you can just look at the assumption of this. So we know that density is equals to mass divided by volume. Similar to this, nuclear density is denoted by density as a rho is equals to, it's a mass of a nucleus, divided by mass of nucleus divided by volume of a nucleus. This is what you call as the nuclear density. Now express this. Density is equals to, density rho is equals to what? It's a mass into atomic number, sorry, mass into mass number of the given atomic constituents. Similarly, volume of a nucleus already we calculated. The volume of a nucleus is 4 by 3 pi r naught a to the power 1 by 3 whole cube. So this is we call as a nuclear density. This is we call as a nuclear density. And you can go with one more step, it is by simplifying this equation. So that is rho is equals to mass into A divided by 4 by 3 pi r naught cube into A. Where A cancel, again you can get the answer as a rho is equals to m divided by 4 by 3 pi r naught cube. It is independent of A. That's a given equation for this density. The next one, where m is also called as, here now we have some notations over there. Why there is a need to go with a small m it is? What is the meaning of the small m? You can call the small m as a average mass of a nucleon. Average mass of a nucleon. Nucleon is the combination of a proton mass plus neutron mass. It's a proton mass and neutron mass. Therefore, we can write, it implies that if it is a combination means what we have to write the nuclear density as a rho is equals to 3 times of mass divided by 4 pi r naught cube. This will give the exact answer is about 2.38 into 10 to the power 17 kg per cubic meter. Same, it is same for all the nucleus. Same for all nucleus. It is same for all the nucleus. Then what are the properties of these nuclear forces? As the PUC first year in the physical world, we have been discussed about the fundamental forces there. Among the four fundamental forces, the third one is the nuclear forces. Nuclear forces are always going to be called as the strongest forces in the nature. This is the first important point. We have there is an strongest forces in nature. Nuclear forces are always called as the strongest forces in the nature. Then second point, nuclear forces are the strongest forces in the nature. Then second one, here we have the second one, this are called as short range force. Short range forces. These are called as a short range forces. And these are attractive forces, causes the stability of a nucleus. Attractive forces as well as the causes the stability. And these forces are always charge independent. And nuclear forces, remember this, nuclear forces are always short range. Short range forces, nuclear forces are always called as what? and a non-central forces. These are called as what? Non-central forces there. Next one. Here, AMU. As you know very well, AMU, atomic mass unit. So atomic mass unit, it is denoted by AMU, shortcut it is. In nuclear physics, the convenient to define there is an atomic mass unit with an abbreviated as a small u. It can be abbreviated. It is denoted as u. Therefore, so hence one atomic mass unit is always defined as it's a 1/12 of mass of 1/12 mass of an carbon 12 atom it is. So this is C612 atom. Therefore, now the masses of an electron is given as mass of an electron is given as 9.1 into 10 raised to minus 31 kg. In terms of AMU is given as 0.00585486 AMU. Then mass of a proton is given as 1.67 into 10 raised to minus 27 kg, and in terms of AMU is 1.007276 AMU. This is we call as the in terms of atomic mass unit, and this is the SI system where we are using there is a mass of an electron as well as the So therefore, as you know very well, so mass of an proton is given as 1.67 into 10 raised to minus 27 kilogram, and 1.007276 as a AMU is the atomic mass unit. Therefore, accordingly now, as you know very well, the Einstein's mass energy relation, what the Einstein's mass energy relation we have, E is equals to mc square. Then we know that m is equals to 1 AMU. M is equals to 1 AMU. And C is equals to 3 into 10 to the power 8 meter per second. And now 1 AMU is always equivalent to 931 MeV, where mega electron volt. Once we solve this, we can get there is an 1 atomic mass unit into C square is equals to 931 MeV. So this is the respective value. And if I going to be adjust for the corresponding speed of light, so C square is equals to 931 MeV divided by EU. Use this formula for the calculation purpose. The next one, it's a nuclear stability. That is what you call neutron-proton ratio. It is nuclear stability is also called as a neutron-proton ratio. Neutron-proton ratio that is given by N by Z ratio. It is also denoted by N by Z ratio. So for a lighter nuclei, greatest stability is achieved. The greatest for a lighter nuclei, the greatest stability is achieved when the number of protons and the neutrons are approximately equals to number of protons and the neutrons are approximately equals to, that is N is nearly equals to Z. Then it can be taken as N by Z is equals to 1. Therefore, heavy nuclei are stable only when they have more neutrons than the proton. So this condition you remember, the stable only, they are only stable when they have more neutrons, than protons. So this condition you have to be remember. The next one we have, there is an mass defect. The next condition we have about the mass defect there. We know that mass defect is always denoted by delta M. So therefore, it is defined as, it is found that it's a mass of a nucleus is always, mass of nucleus is always less than the sum of masses of its constituent nucleons in free state. This difference of masses is called mass defect. Hence, mass defect in mathematical form we can write delta M is equals to sum of masses of nucleons. Minus mass of nucleus. Therefore, delta M mass defect is given as delta M is equals to, it's a Z mass in proton plus A minus Z into mass of a neutron. Close the bracket and capital M. This is the formula we are using for calculating the mass defect. Where capital M is called mass of a nucleus. This is we call mass of nucleus. The next one we have packing fraction. It's a packing fraction. Next we have there is a tacking fraction. Tacking fraction is denoted by F, small f it is, and defined as it's a mass defect per nucleon. Mass defect, mass defect per nucleons. Mass defect per nucleons is called packing fraction. Hence, F is equals to delta M divided by A. And it can be written as what? Capital M minus A divided by A. Where M is called mass of a nucleus, A is called as a mass number. The next one, the binding energy of a nucleus. Binding energy is defined as always, it's the energy required to bind the nucleons inside the atomic nuclei. Is called as a binding energy. Therefore, binding energy per nucleon is given as it's a binding energy per nucleons. Binding energy per nucleons is given as it's a mass defect into 931 MeV divided by it's a A is equals to into what the equation can be written as mega electron volt divided by nucleons. This is the binding energy per nucleon. The next, binding energy per nucleon. Remember the condition here. The binding energy per nucleons is directly proportional to stability of nucleus. Stability of nucleus. It's a stability of nucleus. So these are the conditions which is related to there is a nuclei. Next, we know that there is an radioactivity is the spontaneous disintegration of a heavy atomic nuclei into daughter nuclei with emission of suitable radiations is called as a radioactivity. And we know that the radioactive sample is going to be emit certain radiations. It's going to be emit certain radiations. Among those radiations, the three different types of radiations we obtained. Among the first one is called as a properties of the corresponding radiations will be noted down here. The first one is called as a alpha, beta, and gamma we have. These are the three different types of radiations we obtained there. Therefore, first one, identity. So alpha particles are emitted by helium nucleus or doubly ionized helium, and beta particles are going to be obtained from fast moving electron. Gamma rays are the photons, which are also called as electromagnetic waves. These are called as electromagnetic waves. Then second one is the charge on the alpha particle is 2e, the charge on the beta particle is minus e, and the gamma rays will be denoted as 0 because these are electrically neutral. Then the third property is mass 4 times of the proton, that is given as the 4 times of the mass of a proton for alpha particle and the mass of an electron, it is massless. Then speed is associated with alpha particle is nearly equal to 10 raised to 7 meter per second. It's about 1% to 99% speed of the light, and gamma rays almost moves with the speed of light it is. Then range of kinetic energy associated with the alpha particle is 4 mega electron volt to 9 mega electron volt, and all possible values between the minimum certain to 1.2 mega electron volt for beta and between minimum value of 2.23 mega electron volt for the gamma rays. The next one, penetration power of alpha, beta, gamma. So first is it's one stopped by the paper. It is only going to be stopped by the paper by the alpha particle, but it is having 100 times greater than that of the alpha particles. The next one, it is 10,000 times, that is 100 times greater than the beta particles, and 30 centimeter of iron or a lead sheet can be stopped by the gamma radiations. Then ionization power, the ionization power associated with the alpha particle is 10,000 times. Then comparing to beta is 100 times, gamma is only 1 or equal to 1 it is. Effect of electric and magnetic field associated with alpha particle is deflected. This is also deflected, but gamma radiations does not deflected for alpha. and beta are going to be deflected by the electric and magnetic field, but gamma radiation does not going to be deflect. The next one, the energy spectrum associated with alpha particle is line spectrum as well as the discrete spectrum. For beta particle, it is always continuous. And for gamma radiation, it's a line spectrum and discrete. Mutual interaction with the matter for alpha particle produces heat, beta particle also produces heat, but gamma radiation produces photoelectric effect, Compton effect, pair production also. Then equation of decay. Here we know that it's a X is called as a parent element, A and Z, atomic mass number and atomic number. When during alpha decay takes place, its atomic mass number will be changes by 4 and number decreases by 2 with production of an helium 4. Similarly, here we know that X, that is what we call as a parent new atom, and this is A and Z, and it will use the A will be remains as it is, but Z will going to be increases by 1 and producing with anti-neutrino. Whereas the gamma decay, you find there is an production of, there is a gamma particles over there. The next one we have, there is an radioactive disintegration law. As you know very well, radioactive disintegration law is always denoted by, it's a rate at which the rate of disintegration of a heavy nuclei is going to be directly proportional to the number of atoms present at that time. So dN by dt is directly proportional to En, and therefore we can write this one as a dN by dt is equals to minus lambda into En, where lambda is called as a decay constant, and hence the final result we got, what is that? N is equals to N naught into e power minus lambda into t. And in terms of masses also we can write, this is in terms of number of atoms, and in terms of mass, m is equals to m naught into e power minus lambda into t, where lambda is called as a decay constant. And in terms of activity A is equals to minus dN by dt. dN by dt is equals to lambda into En. Therefore, it can be written as A is equals to A naught into e power minus lambda into t. This is for activity, and this is in terms of mass, and this is for number of atoms. Then what unit of radioactivity is becquerel, Curie and Rutherford. 1 becquerel is always equals to 1 disintegrations per second, and 1 Rutherford is always equals to 10 to the power of 6 disintegrations per second, and 1 Curie is always equals to 3.7 into 10 to the power 11 disintegrations per second. And you know very well, as we taught in the earlier class, that is half-life of a radioactive sample. Half-life is nothing but what? Where the disintegration of half of the atoms from its original is called as a half-life of a radioactive sample. Then it can be given as a T half is equals to 0.693 divided by lambda. This is called half-life of a radioactive sample. Then we know that mean life or average life. Mean life or average life is denoted as a tau is equals to reciprocal of a decay constant. Reciprocal of a decay constant is called as a half-life. In terms of it's we call as a mean life of a radioactive sample. Then uses of these radioactive samples are, one is first one used in medicine purpose. In medicine, used in medicine. Second one used in archaeology, and third one used in agricultural conditions there, and number 4 in tracers, and fourth one as a tracers, and fifth one it is used in industries. And these are the conditions which are related to the radioactivity. Now we have to solve some questions which is related to the first question. We have, there is a density of carbon nucleus C612 is. So we know that as I taught in the previous, the density will be remains as it is unchanged, and as given the earlier value, the density will be, it's a 2.4 into 10 raised to 17 kg per cubic meter. This is the answer for the given question. Already we have solved this condition there. Second question now. The second question, for the decay of nucleus, the possible reasons is neutron-proton ratio too high, neutron-proton ratio too low, size of the nucleus is very large, all of this. As once there is a neutron proton ratio too high, neutron proton ratio is too low, size of the nucleus very large, all of this. You see the condition there. The first one, as you look out, there is an, when neutron proton ratio is too high, beta decay takes place, and the neutron proton ratio is too high, beta decay will be takes place. Yes, it's a correct answer. Then you see that when neutron proton ratio is too low, there is a positron emission also takes place, and this is also correct answer. Then you see, when size of the nucleus is very large, alpha decay takes place, and the size of the nucleus is very large, and hence the option number 4 is the correct answer. It means all are the correct conditions there. The next question. Look at the question number 3. The density is denoted by D of a nuclear matter varies with the nucleon number A as you know very well. The density is given as D is equals to A into atomic mass unit divided by volume is given as 4 by 3 pi R naught cube into A. Then this whole value, if I substitute, then what I get now here? So this is density is directly proportional to A naught. Hence option number 4 is the correct answer. Very good. The option number 4 is the correct answer. So go for the next question. Here we go with the next question, that is, when an electron-positron pair annihilates, the energy released is about. We know that energy released can be given as in terms of, it's a E is equals to 1.02 mega electron volt. Mega electron volt, 1 electron volt is equals to 1.6 into 10 to the power minus 19 joules. This you have to convert in terms of joules it is. Then substitute this value. E is equals to 1.02. 1 mega is equals to 10 raised to 6. This is 10 raised to 6 into 1.6 into 10 raised to minus 19. E is equals to 1.6 into 10 to the power minus 13 joules. The answer is B. Then go for the next question. A heavy nucleus at rest breaks up into two fragments, which fly off with the velocities in the ratio 8:1. The ratio of radii of the fragments is, we know that velocities in terms can be given as, so this is the mass you have, capital M, and now it's going to breaks up into two daughter. Say this is M1 and say this is M2, and this is moving with some velocity as a V1, and this is moving with a velocity V2. And according to the law of conservation of energy, what you have, M1 V1 is equals to M2 V2. So what you have the condition there? So according to the law of conservation of energy, M1 V1 is equals to M2 V2. And now we can find out the velocities. Say therefore, it's a V1 by V2 is equals to, it's M2 by M1. M2 by M1. Then you know very well V1 by V2 is equals to, M2 by M1 is given. How much it is? 8 by 1. So this is 8 by 1 is equals to equation 1 it is. Then radius r is going to be directly proportional to a to the power 1 by 3. Then simplify this, what you get? So it's r1 by r2 is equals to, it is a1 by a2 whole to the power 1 by 3. So therefore, once you solve this, you'll get what? 1 by 2. It's a 1 by 8, you get 1 by 8 whole cube is equals to, it's 1 by 2. So option number 1 is the correct answer. Option number 1 is the correct answer there. So next question. The ratio of radii of nuclei aluminum 2713 and titanium 12552 is approximately 6 is to 10, 13 is to 52, 40 is to 177, 14 is to 7. Then you know very well the formula. Once again we are applying r is directly proportional to a to the power 1 by 3. Then you know very well r1 is equals to some constant a to the power 1 by 3. R2 is equals to, it is k into a2 to the power 1 by 3, and divide both the equation. R1 by R2 is equals to it's a1 by a2 whole to the power 1 by 3, a to the power 1 by 3, and you know the given values. It's at 27 and 125. So R1 by R2 is equals to 27 divided by 125. So therefore it is 8 by 5 is equals to 6 by 10. Hence option number 1 is the correct answer. That's good. The two copper 64 nuclei touch each other. The electrostatic repulsive energy of the system will be 0.788 mega electron volt, 7.88 mega electron volt, 126.15 mega electron volt, 788 mega electron volt. The first we have to find out r is equals to r naught into a power 1 by 3. So this value will be equals to what? So this is 1.2 into 64 whole to the power 1 by 3. And this is equals to this is 4.8 Fermi meter. We got the answer, the distance. Then nuclei, the distance between the two nuclei can be given as r is equals to 2 times of capital R. Then the potential energy is given as U is equals to K into Q square divided by R. So potential, this K value can be given as 9 into 10 to the power of 9. Then charge is given as 1.6 into 10 to the power minus 19 into 29 whole square copper. So therefore whole divided by, it's a 2 into 4.8 into 10 raised to minus 15 into 1.6 into 10 raised to minus 19, because they are converting in terms of mega electron volt. So this answer will be equals to 126.15 mega electron volt. Option number 3 is the correct answer. The next one we have, a particle is moving with a velocity of 1 by 10th of that of the light will cross a nucleus in about. And we know that, so time period can be given as t is equals to 2 times of r into v. Time period is equals to 2 times of r into 2 times of r divided by v. And as you know very well, 2 into 10 to the power of 2 into 10 to the power of minus 15 meter divided by 3 into 10 to the power of 7 meter per second is the speed, and hence we can substitute this value will be equal to 2 by 3 into 10 to the power of minus 22. So this is the answer. Very good. The next one we have, a sample contains large number of nuclei. The probability that nucleus in the sample will decay after 4 half-life is. As you know very well, the decay formula can be given as it's n by n naught. N by n naught is equals to 1 by 2 times of n. And as the corresponding value is always equals to q, where n is the number of lives, where q is equals to, it's 1 by 2 times of 4 is equals to 1 by 16. 1 by 16. The probability of that nucleus will decay up to the value of p. So it is given as 1, and then minus q is equals to 1 minus 1 by 16. Solve this equation, we can get 16 minus 1 divided by 16 is equals to 15 by 16. Option number 3 is the correct answer. The ratio of radii of nuclei A713 and AXA52 is 3:5. The number of neutrons in the nuclei of X will be. And you know very well the formula. Once again we can apply simple, that is R is directly proportional to A to the power 1 by 3, and you can apply 3 by 5 is equals to 27. It's a 27 divided by A whole to the power 1 by 3, and A is equals to will get 125. A is equals to 125. N, so there is a neutrons in the nuclei will be given as is equals to A minus Z is equals to 125 minus 52 is equals to 73. So this X will be 73. The next question, distance in the free space at which intensity of 5 electron volt neutron beam reduces to half will be nearly equals to, that is take pi by 2 is equals to 12.8 minutes, 6,000 kilometer, 1,200 kilometer, 18,000 kilometer, 24,000 kilometer. So therefore we know that the kinetic energy half mv square is equals to, it can be written as k, and therefore 1 by 2 into mass is 1.6 into 10 raised to minus 27 into v is given. How much is the, whether we have to calculate the velocity, and the intensity is given. How much it is? 5 electron volt. 5 into 1.6 into 10 raised to minus 19 joules. And v is equals to, we get, it's a 31 kilometers per second. And we have to calculate the distance. We know that distance is equals to velocity into time. So therefore velocity is 31 into 10 raised to 3. Time is given as a 12.8 minutes. 12.8 minutes, minutes can be converted into seconds, that is 60 is equals to 24,000 kilometer. Option number 4. In radium-226-88 nucleus, there are 138 protons and 88 neutrons, 138 neutrons and 88 protons, 226 protons and 88 electrons, 226 neutrons and 138 electrons. So this can be calculated as number of protons is equals to 88. Therefore, and atomic mass is given as 226. And therefore n nucleons is given as A minus np is equals to 226 minus 88 is equals to, it's 138. So 138, option number B. That's good. The next one, here we have a question next. The mass number of helium is 4 and that of the for sulfur is 32. The radius of sulfur nucleus is larger than that of the helium by times. So this, once again we have to apply the formula for that. R is directly proportional to A to the power 1 by 3. Then for this is sulfur divided by R for helium. This is equals to A sulfur divided by A helium whole to the power 1 by 3. And this can be written as 32 by 4 whole to the power 1 by 3. So this is 4 ones are 4 eights are. This is equals to 8 to the power 1 by 3. This is equals to 2 cube whole to the power 1 by 3. 3 3 cancel. Hence the answer is 2. Option number 3 is the correct answer. A nucleus ruptures into two nuclear parts which have their velocity ratio equals to 2 is to 1. What will be the ratio of their nuclear sizes? And as you know, there is an law of conservation of mass, and law of conservation we get there is an m1 v1 is equals to m2 v2. Then we know that m1 by m2 is equals to v2 by v1, and we know that in terms of mass can be written as mass is equals to volume into density. So in terms of volume into density, we have to be express the mass. That can be given as 4 by 3 by r1 cube into density whole divided by 4 by 3 times of pi r2 cube into density is equals to velocity v2 by v1. So 4 by 3 pi, 4 by 3 pi, density will be cancelled. Then we get this is r1 by r2 whole cube is equals to v2 by v1, v2 divided by v1. Then we know that, so this r1 by r2, r1 by r2 is equals to, this is v2 by v1 whole to the power 1 by 3. So r1 by r2 is equals to v2 by v1 is given. So this is a 2 is to 1, that is 1 by 2, 1 by 2 whole to the power 1 by 3. So therefore the answer is option number 2. That's right. If mass of a proton is 1.008 AMU, mass of a neutron is 1.009 AMU. Then the binding energy for nucleon of a barium 94 mass is 9.012 AMU will be. And you know very well, so this can be given as mass defect delta M is equals to, it's a 4 times of mass of proton plus it's a 5 times of neutron minus capital M. Therefore energy is equals to mass defect into 931 MeV, binding energy per nucleon. Binding energy per nucleon is equals to mass defect delta M into 931 MeV divided by 9. Hence once you solve this, we can get the answer 3, that is 6.7 into 10 to 6.72 into 10 to the power of 6, that is in terms of electron volt, or you can also write as a mega electron volt. A nucleus disintegrates into two nuclear parts which have their velocities in the ratio 2 is to 1. The ratio of their nuclear sizes will be, the nuclear size ratio will be as it is, as we did in the previous problem. There is a complete detailed steps we did, and now we go with the shortcut, that is m1 by m2 is equals to, it's a v2 by v1, and we can write directly it is r1 by r2 whole cube is equals to, it's a 1 by 2 whole to the 1 by 2, v2 by v1 is 1 by 2 we got. So therefore it's r1 by r2 is equals to, it's 1 by 2 whole to the power 1 by 3, and then r1 by r2 is equals to 1 by 2 to the power 1 by 3. Option number 3 is the, sorry, it's one, option number 2 is the correct answer. So next we go with the question number 17. If mass of a proton is 1.008 AMU and mass of a neutron is 1.009 AMU, then the binding energy per nucleon of barium 94, mass is 9.012 AMU will be. So this we can write, the binding energy can be given as binding energy is equals to, it's a 4 into 1.008 plus 5 into 1.009 minus 9.012 into 931.50 MeV. Then we can get the answer as 60 point, binding energy is 60.55 mega electron volt. Then binding energy per nucleon is 60.55 mega electron volt divided by A is given as 4. So 4 ones are. So once you solve this, you can get the answer as 6.724 into 10 raised to 6 electron volt. Converting in terms of electron volt. It is if we obtained in terms of joules and you can just convert in terms of electron volt, we can get the answer as a C, 6.7. The binding energy per nucleon of a following nuclide is maxima. Which is the binding energy for the following nuclide is maxima. As you know very well from the binding energy curve, the binding energy curve will explains about there is a stable, unstable and highly unstable. This is we call as a highly unstable, and this too will be considered in stable, and this is the one will going to be having maximum stable condition. The option number 3 is the correct one. When uranium-235-92 undergoes fission, 0.1% of the original mass is changed into energy. How much energy will be released if 1 kg of uranium-235 undergoes fission? 9 into 10 to the power of 10, 9 into 10 to the power of 11, 9 into 10 to the power of 12, 9 into 10 to the power of 13 joules. As you know very well, by using the relation E is equals to delta M into C square, and E is equals to change in mass is given. The change in mass is 0.1 by 100 into, it's a 1 into 3 into 10 to the power of 8 whole square. Solve this equation. You can get the energy as a 9 into 10 to the power of 13 joules. The option number 4. Option number 4 is the correct answer. A radioactive substance decays to 1 by 16th of its initial activity in the 40th days. The half-life of a radioactive substance expressed in days is. We know that the formula will be N is equals to N naught into 1 by 2 times of small t into t half. So therefore, N by N naught is equals to 1 by 16, and this can be written as 1 by 2 times of 1 by 2 times of the time period is given as a 40th day, 40 divided by t half. Then once if I solve this equation, you can get the answer as a t half is equals to 10 days. T half is equals to 10 days you will get. By solving this, you will get a 10 days. Atomic power station of a Tarapur has generating a capacity of 200 megawatt. The energy generated in a day by this station is. The energy generated in a day is. So we know that energy is equals to power into time. So power capacity is about 200 megawatt. 200 mega is 10 raised to 6 into time is generated in a day. In a day means 24 hours into 60 into 63,600. So this can be obtained as a 1728 into 10 to the power of 10 joules. Option number 4. When an electron revolves around the nucleus, then the ratio of magnetic moment to the angular momentum is, we know that angular momentum is given as L is equals to, in terms of Bohr's quantization rule, L is equals to NH divided by 2 pi, and this is equals to mvr. Then magnetic moment is given as mu or small m, sorry, mu or capital M is equals to, it's a current into area. Then it is equals to E divided by 2 pi r, E divided 2 pi r into nu into pi r square. Area is given as a pi r square. Hence, it's a magnetic moment. Mu is equals to E by 2 into L by M. Hence, it's a mu divided by L is equals to E divided by 2M. So option number first is the correct answer. In question number 23, the binding energy of a deuteron is of order. The binding energy of a deuteron is of order. It's almost equals to 10 to the power of 6 electron volt. It's a direct question it is. So this energy will be directly related to the energy associated with the deuteron in the binding energy curve is 10 to the power of 6 electron volt. The next question. So half-life of a gold is 198 is 2.7 days. The probability that any gold 198 nucleus will be decay in 1 second is. So hence we know that decay constant value lambda is equals to 0.693 divided by T half. It's a T half formula we have to be applied. Then it's equals to 0.693 divided by, so half-life is given as what? 2.7 days. 2.7 days is given, and convert in terms of seconds and hour. So this is what we call 0.693 divided by 2.7. So 2.7 into 24 hours into 60 into 60 seconds. Then we can get lambda is equals to 2.97 into 10 to the power of minus 6 per second. 2.9. 2.9 is nearly equals to 3. That is option number 2 is the correct answer. If N naught is the original amount of a substance of a half-life period, T half is equals to 5 years, then the amount of substance left after 15 years is, we can apply the direct formula here. So that formula is N is equals to N naught into 1 by 2 times of, it's a 15 by 5. 15 by 5. Then, so if I solve this equation, N is equals to N naught into, so this is 5 ones are 5 3s are 15. Therefore, 1 by 2 whole to the power of 3. Therefore, N is equals to, this is N naught by 2 to the 4 to the 8. It's a 8. So option number A is the correct answer.